Welcome everyone to Quanterall's first functional programming event. We're happy to see you here, and we hope to be doing more of these in the future. My name is Rickard Andersson, and I'm going to be talking about guarantees in software development. What they mean, how we should think about them, and how we can think about them, and so on. Brief stuff here about me. I love programming. I have 4 cats. I also love those. I am particularly fond of Beam languages. I say Beam languages because, of course, we have many we can use. ML descendants and Lisps. This is maybe an odd mix. Probably not if you know me. What feels like a lifetime ago, I started programming in C++. It was a bad time. And along the way, I picked up a few languages that I more or less like at this point in time. So, what are we doing here today? Well, we're going to talk about guarantees and intent and sort of try to, in some ways, concretize what that actually means, right? And talking about what should we expect from our guarantees, and if we have certain things that we can say about our guarantees, what does that give us, right? And we're going to look at some different types of guarantees and sort of talk about how we use these, how do we interface with these, and so on. So let's do some definitions of stuff, because we have to sort of, a guarantee is something that we can, provided some very basic assumption that sounds ridiculous, we can say that this is true, right? So given a working compiler, this function takes an integer and returns an integer. We can guarantee that, right? Given the Erlang runtime system and OTP work as they should, this process will restart to a known stable state. Right? So I say sort of a basic assumption, right? Because everything is built on assumptions if you think about it, right? We can have some solar flare that basically flips a bit in your memory and stuff basically doesn't work anymore, right? We don't expect those, right? Should we? Maybe. An intent, however, is something that really only implies something to be true, or it implies something to be the case, right? Where we are, in some sense, signaling what is going on. We're not actually guaranteeing what's going on, right? Usually, some amount of this contract in this process is left up to the user of that code or that system, right? The intent is for you to use it this way, but all bets are off if you do something else, right? So given that you passed a valid argument to this function, it should return the same type back. But nothing checks that, right? This is, in some sense, an intent more than it is a guarantee. We can't actually say that this is guaranteed, right? Given that you're running dialyzer, and it can find a way to disprove your types, you'll know whether this is a type error or not. That's a long if. Like, it's very hard to rely on this, to be honest, in practice. So there are some aspects of guarantees that I think are interesting. I don't know if temporality is a word, but we're going to use it, right? We're going to say it is. When does something happen? When do I know that I've broken some contract, right? When, in the sense of, from writing this code, when did I actually get to know that, no, that's wrong? Like, that's a wrong assumption, right? That's an important aspect of this, right? We also have transitivity, where if I build something using this guarantee, what guarantees am I providing, right? This is an interesting thing, because sometimes we use a guarantee and it gives us nothing in terms of the thing that we built, right? That thing does not have the same guarantees as what we used to build it, right? And also, is it explicit or implicit, right? Is this guarantee something that just sort of exists, unstated, unknown, unless someone tells you, right? Usually, we would prefer explicit, to be honest, or we should. So, there are some interesting guarantees in Erlang. Erlang, of course, is not, it's a dynamic language, but it does come with a lot of guarantees that are very interesting, right? So, supervision trees are start at depth first, preemptive scheduling, pattern matching and guards, and we're going to look into these, sort of what they mean. So, if this is our supervision tree, first of all, actually, How many here know Erlang and sort of Erlang-like things? Okay, this is a good number. I guess I should have expected this, right? So if we have the supervision tree, this is not necessarily representative of what you would see in your app, but here's the thing we have, right? So squares are supervisors, and just other processes are rounded, right? And so here's what's going to happen in our supervision tree, right? We're going to start the log supervisor first. Then we're actually going to start the file log supervisor. And then we're going to start all of the children of that, right? Then we're going to start the web log supervisor, and so on. And this is not negotiable, right? This is something that just sort of is, and we have to work with this. What we actually can get, though, is that we can guarantee that the subsystem that is started after something else and relies on the earlier systems, we can rely on the earlier things being started in time, right? So we get this guarantee from the runtime system, from the actual just OTP, right? And this means that when we actually deliberately make our supervision trees, then we will get this guarantee and be able to use it, right? So there's an interesting thing, though, right? Is this transitive? Can someone tell me if this is transitive or not? Is it a transitive guarantee that I am making a supervision tree, and I'm getting this guarantee here? When I provide someone with a supervision tree, am I going to get the same qualities back from this? It is, right? Because recursively, we saw basically, if you go back to this supervision tree here, right? All of it is trees, right? So the log supervisor has 2 subtrees, right? And these are all started in sequence. So it is transitive in nature, right? Is this guarantee explicit, though? It looks explicit, right? It looks explicit in the sense that we have staked out our stuff. But at no point are we talking about the guarantee itself, right? And that's an interesting aspect of this, right? We have to know that this is the case, right? We can't choose. And we certainly never have anything that checks for us. Oh, are we abiding by this? In some sense, this is actually, you can't not do this, right? So in some sense, maybe those are the guarantees that we never have to talk about, because we can't actually invalidate them, right? There are guarantees where we are saying something, right? And then we are invalidating that assumption. And then we need to know about it, right? But there's an interesting aspect here where we don't necessarily need to talk about this, because we can't actually break this. We can use it badly. And that's basically it, right? We can start our web server before everything else, and it will try to use resources that exist in other parts of the supervision tree, right? So we can use it badly, but we can't actually break the guarantee itself. So let's see. Yeah, a small primer kind of ish on preemptive scheduling, what it means. All of our processes, they exist at the same time. They run at the same time, ostensibly, right? We will have as many running at any point in time as we have cores on the machine, basically. The interesting part here is actually that we can see here, a process has a set amount of reductions that it's allowed to actually consume. It's almost like fuel, right? You can view a process effectively in Erlang as basically it's a car that runs until it's out of fuel, and then it has to take a pit stop, and then it can run again, right? The scheduler is the system that basically decides this, right? The guarantee that we have here is effectively that all processes will basically play nice with each other, regardless of what they're doing. There's a caveat there. If you use a function, every function consumes fuel, reductions, right? If you use a function that for some reason has an incredibly long runtime and is not built out of other sub-functions, right? You actually end up in a situation where that one function call just counts as much as a very small function call. So adding 2 numbers together, for example, will consume the same amount of fuel in some sense, maybe as term to binary on a very large term. And term to binary, of course, is the thing that takes a random, basically any term in Erlang and turns it into a binary. So we can store it somewhere, or we can do something with it. We can send it over the wire, for example. Term to binary on a massive structure will, of course, take a lot of processing power. But it will basically count as one function call. And so what we end up with is, if we have a lot of those calls, well, now we're kind of breaking the guarantee that we are playing nice with other things, right? But this requires you, of course, to use functions like that. It requires you to end up in those situations, right? For the most part, our code will actually, it is guaranteed to work nicely with everything else. It depends kind of, when you find yourself in these situations, yeah, it can be very hard to debug, that you're kind of fooling the scheduler, that you, oh, I'm just doing a little bit of work, don't mind me. I'm just gonna take this massive tree and turn it into a binary. It's fine. But yeah, this is a guarantee that we do get from the scheduler, the runtime system, in fact, right? And it's an interesting guarantee, right? We don't actually have to do much. We can use it badly, again. We can use everything badly, but it's an interesting kind of guarantee that exists in the background, sort of. So yeah. Let's look at some code, though. We're going to talk about pattern matching and stuff, type systems. So let's see. Can everyone see this? Okay. So here we have some Erlang code. And we have a function down here, parse pieces, that basically takes a binary and splits it up in binaries of size 20 bytes, and so on. And we're using a guard here. Can someone tell me what we're guaranteeing with this guard? The guard itself, not the type. Yes, that is the actual guarantee. What are we actually guaranteeing in a meta sense, in some sense, right? Because we are, in fact, saying, hey, this has to be divisible by 20, right? It's a core thing here, right? We are actually, what we're taking is a binary that represents pairs in BitTorrent. And these pairs, or these pieces of a file, sorry, in BitTorrent, these are SHA-1 hashes, right? They're 20 bytes in size. What are we actually guaranteeing here, though, right? So if we look at this function here, it has two cases, right? The first one, we have a guard. What does a guard actually do in terms of guarantees? Because it actually has nothing to do with types, right? It is an assertion, right? What does an assertion do in some sense, right? It basically says, at this point in time, we will check a thing. If it's true, we will continue. That is what this is doing. This guard, all guards, all pattern matching, say the code below will only run if this is true. Right? That's the guarantee that we get. So that's an interesting aspect, right? It doesn't talk about types. It says, I have an assertion to make. And then it says basically, the code below will run if that assertion is true. And then we can provide effectively a fallback, right? This is the fallback. Here's what to do otherwise. Or we can have other interesting assertions, right? This is an interesting guarantee. Is that a transitive guarantee? Am I basically able to kind of, how do I relate to this when I use it, right? If I use this in a function, does that tell me stuff about the rest of what I have? I would contend that no. It's kind of not transitive. It's just a very small thing. And of course, it will change the behavior of our program, so it's not that it doesn't do anything, but we can't build other guarantees out of this, in some sense, right? We can use it, but it's hard to kind of use with other stuff, right? So, we have specs here, right? We have these specs that talk about types and so on. I'm going to uncomment this here. Here I'm taking an integer and turning it into a binary. The eagle-eyed among you will see that this is actually wrong. But we are not getting that information, right? So we have a type system that we're using here, right? What's the temporality of the guarantee that I'm using my types here? Right? I have a type system, so I can say basic stuff like this is a string, this is an integer. They shouldn't go together, right? What's the temporality of my current situation, my current guarantee? It's never. My dialyzer is not working, right? When you have something that requires something else to kind of work like this, the temporality can be never, right? That kind of guarantee is hard to use, right? It's not very easy. Let's see. Here we have some Elixir. And this is an interesting piece of code because, not because it's good, but because this is effectively kind of what you see all over the place, right? Can someone see something that's kind of awkward about this? I mean, there's tons probably, but something that should stand out maybe in terms of guarantees. I'm obviously trying to use types here, right? So we're using dialyzer. We've already accepted that there's some level of dialyzer has to work. We have already accepted this in our life, right? But what is the mistake I'm making here, right? Can someone see what that might be? I have types, but they are aliases to other types. And this doesn't actually do anything. You would be excused for writing this code because it's all over the Elixir standard library. Type T for a destination is a path T. Do you know what path T is? Path T is basically a type alias for string, also an IO list, and so on. So it does serve a purpose to have that type, but it's not exactly type safety. It doesn't actually do much in terms of this. We don't have a lot of stuff that sort of is very distinct, right? And if we want distinct things, we actually have to, in some sense, do things like use opaque and so on. And so you've made the decision to use opaque, right? Opaque here is basically saying nothing outside of this module that I'm using this in can see what this is, right? So instead we have to talk about things like, well, no, we have the source type. We don't have a path T, right? When I made these opaque now, these other places are lighting up because they don't know what that means. They know that they have a source, but they don't know that that means that we have a string, right? So what we actually have to do is, actually, let's do spec wrap. Exactly. Not quite. And here we should do a spec unwrap. Oh, hello. There you go. Who needs macros, right? When you have AI. So, that was a joke, by the way. I'm not saying. So, anyway, here we actually have to now say some extra things. Actually, yes, here's where we want to unwrap. In fact, we want source unwrap here. And source unwrap here. No, destination. So, here we're also going to say that these functions now that return source and so on, we're going to say source.wrap and destination.wrap. This is so that we are now taking this string and making it into source and destination types, right? Here's the original bug that existed when we were using type aliases. Link file expects a certain order of arguments here. We had the wrong order. Finally, we are actually at a point where we can actually say this is now, in some sense, correct. So what I'm going to do here is, I'm going to put that there. So now we're fine. But we kind of had to go a little bit, to get there. So what I'm going to suggest here is actually to replace this. This is what I mean by I was joking about AI. This is a macro that just does this. It defines wrap and unwrap for defining opaque types, so that we can actually have effectively just this, and then we get these wrapping and unwrapping functions, right? So the idea here is not necessarily to pepper your code with a bunch of extra stuff that doesn't have anything to do with the problem. The idea is to maybe illustrate that this idea with type aliases doesn't actually give us much, and maybe there's another way to do the same thing and actually have that happen safely. Because the original problem we're solving when we do this is basically I have two strings and I don't know which one is which. Right? So what we're doing here is we're saying this one is definitely the destination of this linking the file. This one is the source, and so on. And this is something we can in fact do safely. There are issues with this, of course, but yeah. So there was a thing in the beginning, right, that I kind of forgot to say because, well, it's not as important to me as guarantees. But we did have a very interesting situation in the beginning. We were very high on intent, kind of, right? Intent, we were describing our intent very clearly. This is a source, this is a destination. That didn't really prevent us from making mistakes, though. And I feel like mistakes are kind of what we keep making. I will actually say that when making this presentation, I found tons and tons of mistakes that are interesting, and so on. So here we have our Erlang code from before, written in Elixir. And so here we actually have working dialyzer, I hope. Oh, we do. Okay, so we have dialyzer working, right? Now, what is the temporality of this guarantee suddenly? Any answer is fine if it involves the words basically now, right? It's basically now, right? We have some guarantee here that I'm trying to use this thing here, which is a SHA-1 hash, so it's a binary, right? I'm trying to use it as an integer, and dialyzer is telling me that doesn't really make sense. I mean, that's provably wrong, right? So the temporality is basically now, right? On save, right? Which is a good place to be, right? We have places that are kind of beyond that. We have, for example, well, on test. And this is mostly an acceptable thing, right? The problem there is the temporality of a test you never write, right, is never. And that's awkward, right? Because we have a temporality that basically we can reach. We have potential for having this be, well, no, my tests run in 20 seconds, for example, or 5. But a test that's never written will simply never give you a guarantee of anything, right? So that's an awkward place to be honest. Does anyone spot a bug here? Is there anything in this code here that pops out? We have basically here we have a return type. Does that match what we're returning? I would argue it doesn't, right? We see the dialyzer is working, but I'm telling dialyzer, or well, I'm telling kind of myself here with my signaling here that, oh, we're returning a list of binaries, right? But what I'm actually doing is I'm returning an integer. I'm returning the byte size of a binary, which is never a list of binaries, right? And I'm also returning 0 in the other case. And this is massively disappointing, right? And I found this accidentally. Dialyzer just doesn't work. I didn't mean to cause this. I haven't done anything interesting here, right? This actually was found accidentally while writing this code, because I was procrastinating for quite some time. And then I wrote the code for this stuff. And I just, yeah, I feel like it's such a beautiful illustration of the issue, right? We see that dialyzer is working. It's actually telling us something more interesting in the other case, but somehow it just stops working, and you can never tell. You can actually never tell. Is it just dialyzer being conservative? Is it dialyzer not working? Is it working somewhat? To all of those is yes. So we can do other stuff, right? We can, in fact, write other code for the beam, right? And so here's our original code for linking files and so on. And this is PureScript, and this compiles to Erlang. And we have effectively the same thing we had before here. But there are some things that are interesting. Can someone kind of spot a difference in terms of, if we look at links file was talking about, okay, here's my input and here's my output. There's an interesting code that kind of is slightly different, right? Can anyone tell me, just shout out, monads, or something, as you do in the grocery. So basically, what I'm talking about is, first of all, this here, we are talking about the existence of effects in our functions, right? There's a common, I guess, misconception, lore, if you will, about Haskell and other languages like it, that the idea is to not have side effects. And that's a beautiful thought in some ways, but I struggle to see the point of a program that does not have side effects. The difference here is really only we're talking about them, right? We're saying in our type here that this does something, right? This does something to the rest of the world. It's basically not referentially transparent. If I link this file now with these arguments and the certain arguments, right? It does not mean that linking that file tomorrow will produce the same result, right? That's why we have effects. And so, if we go a little bit further with this, we can actually do even more. And so, before, we had this situation where we're talking about effects in our functions, right? But we basically are saying, yeah, I'm doing effects, right? And we're not saying sort of, what effects am I doing? We're just saying blanket effects. Okay, I'm getting shut down here, I think. And here we can do this. That's what I'm going to say about that. So let's walk over to the slides again. So there are a few takeaways from this. Temporality is important for certain types of guarantees. The temporality of guarantee that you have to install something for, run something for, is sometimes never important. Transitive guarantees allow us to build bigger and better guarantees. Explicit guarantees live on a spectrum where we can sometimes say more or less, right? We can say more, that means we can get more out of them, right? The guarantees we get are more precise, and so on. Oftentimes, this is basically, we are disallowed from doing certain things, right? And that's actually what we want, generally speaking. We want to restrict the programs that we can write so that we can write them more precisely. Thank you.